Hello and welcome to more Haskell live coding. I'm going to start with an apology. It's just going to be quite a painful episode to watch because I've lost the ability to type. And it's my own stupid fault. I've been a bit of an idiot, but I've been experimenting with keyboard layouts and I've now gotten to the point where I can't really type on any kind of layout at all, which makes life somewhat difficult. So I'll struggle through this episode. I hope it's not too bad to watch. I'll try and stick to some theory perhaps to try and make it a bit easier, but generally speaking my typing is going to be all over the place. It's the fault of this guy, I guess, ultimately, Ben Valek. He does some YouTube videos, including stuff on trying to push the limits of keyboards, and he has this keyboard with a 16 key layout. I haven't quite gone to this, but I've gone to a 22 key layout, which is still not enough to get all of the letters onto a single layer. So I'm trying to learn to type on this layout where the top letter is the letter that comes out when you press the key, and if you hold down this modifier you get the bottom key on there, and there's some double tap stuff. And it's actually a bit worse than that because there are also symbols and numbers on the keys, so it's just taken me a long time to learn this. And I've moved all the keys around as well, which means that I've got basically no muscle memory at all for this. So it is going to be a little bit painful, and I apologize in advance for that. Okay, plan for tonight. I was working on local variables last week, just finishing that off. So we can basically refer to a variable, and the equivalent instruction in the bytecode is going to be to load that variable from a particular address in the stack. Right, let's take a look at this. So load is taking an offset into the stack. So offset 0 will be the first number, which will be actually it's not, it's going to be the 5 that's pushed on because stuff gets pushed on backwards. And 2 is going to be this offset. Is that right? Doesn't look right. No, 0 must be this side. Okay, so we're offsetting from the back of the stack. So the first thing it pushed on would be 0, and the second thing is 1, and the third thing is 2. Okay, so you can pull those two numbers off and then add them together. And that's essentially what I'm going to be using for passing parameters into functions. So I want to go back and have a look at trying to finish off some of the function stuff by passing data into functions. I've got this test for return just works. So we call the function, we give it the address that we're going to jump to, which is this address. It does some stuff, so it pushes number 5 onto the stack, and then it returns from there, and we take the last value of the stack from the function and push it back onto the stack after we've returned. So that's good for getting values out of the stack, but we're going to look at getting values into functions as well. Return is good for getting values out of a function, and the thing I want to look at today is getting values into a function. I've just noticed that I haven't committed this stuff, so let's give that a go. Is it just load? That looks like load. That looks like load. And that looks like load. So I can commit this. And what did I do here? I guess I added an instruction for loading. Yeah, wasn't too bad. I'll just push upstream. Okay, back to where we were. So let me try and bring up just the plan. Yeah, I need to get rid of that. That was to do with local variables, but we can maybe go back and look at this idea. So we could define a function. We don't have conditionals yet, so I can't implement this kind of branching stuff, but we can maybe write a simpler function. Oops, what's happened there? Something strange has happened. My fingers are off by 1, that's what happened. So we could write a simple function and we could just call it add, for example. And it could maybe take a couple of arguments. So it could take, let's say x and y. X and y, y is there, okay. And in this function, we could just return x plus y. And then we could call it by saying add, I guess we can use some brackets here, and we can, I guess, use the same numbers. So we could say 2, oops, look at comma there, 2 and 5. Okay, so what's going to happen in terms of converting this into instructions? The first thing we're going to do is we need to evaluate these 2 arguments, and they're just simple numbers. They could be expressions that need to be evaluated in their own right, but for this example, they're just simple numbers. So we can then just say, I guess we could say push and then the value 2, and then push and then the value 5. So it's going to be our first 4 bytes, first 2 instructions. And then we're going to call, and we're going to call the address of wherever this function ends up. So what I previously had is, what's else going to be? It's going to be 1, 2, 3, 4, 5, 6. Then we'll have a halt, which will be 7, and then the actual address will probably be 8. I guess it doesn't really matter, that's not completely right, but hopefully it'll be 8. And then we need to halt after that because our program's finished once we return from this function. So we can just halt at that point. So that's 1, 2, 3, 4, 5, 6, 7, and then instruction 8 is going to be the start of the function. So the function is, it takes 2 arguments, and the first thing it does is it gets the value for x. So that's going to be load, and then the address of x. Now I'm going to initially set this, I think, to be -1. So -1 will be the first parameter passed in. And then we're going to load the second instruction. So I'll set this to be -2. So we'll load the second parameter even. So we'll load those 2 things, we'll put them onto the stack. And then once we're done, we just add them together. And then we return from the function. So that's what I think my compiled version is going to look like almost. So I think we're going to have to put something after call to tell it how many parameters we have. But maybe we don't. Let me think this through then. So if we think about the stack, initially, first thing we're going to do is push the number 2 onto there. So the stack just becomes 2. Then we push number 5. So this, oops, this is our stack. So we had 2, we pushed 5 on as well. Then we call address location 8. So what we push onto the stack at that point is the return address, which would be this next instruction. So it's 1, 2, 3, 4, 5, 6, 7. So we end up with 7 on the stack, and then the 5 and the 2 that we had before. I actually think this is slightly wrong if I'm pushing this way. Because what I want to end up with is easy access to this in relation to where the stack is. Let me draw the stack the other way because it might make a little bit more sense as to why this is broken. But if we initially push 2 and then we push 2 and 5, and then when we call, the VM will end up pushing the return address, which is 7. And I guess at this point, this is it's not only the stack, but this is the stack frame that we're currently operating in. Oh, sorry, no, that's not quite true. This was the stack frame previously. So when we call our function, one of the things we're doing is we're setting the stack frame to start after this thing has been pushed on. So we actually end up with our stack frame being this. We have nothing in there at the moment. Then I want to load -1. What I'd really like to do is, I know where this address is, this return address. So what I'm thinking I can do is put the first argument just before it. And then the second argument will be before that. So this -1 can count back from this position. This is the return address, but it's just at the very beginning of our stack frame, or just outside it. Actually, I think we point to this. So I kind of think that the stack frame is actually that at the point at which we call it, and this is our return address. So what I'm thinking is when we see add 2 and 5, we should push them in reverse order. So I think the instruction should be, push 5 and then push 2. So that our stack ends up looking like this. Okay, so then when we get to load -1, we can say this is the boundary of our stack frame. So I will look at the position before it. So our stack will then be looking like this, and then we start the stack frame for the function, and we load -1, which will then load 2 into that position. Then we load -2, so that should be nice and easy. 7, 2, and 5. Then we call add. Add pops 2 things off the stack and adds them together. So we'd end up with 7 and then coincidentally 7. Then return takes this last value and remembers it, grabs this as a return address, throws away the stack frame, and pushes the result back onto the stack. So what we end up with is 5 and then 2 and then 7 on the stack. So it's a bit annoying, my return address is also 7. This 7 is a red herring, this 7 is the one that we're interested in. So actually, in this example, I don't need to know how many parameters I'm passing in. Right? When we're writing the compiler side of this, we will need to worry about this. We'll need to say there are 2 parameters. We know we need to go back and get 2 previous values. And we know that we need to evaluate this and take the result of that and push it onto the stack. We need to evaluate this and take the result and push it onto the stack. So this was actually, instead of being 5, this was 1 plus 4. For example, it would need to work out the value of 1 plus 4 by pushing 1 and 4 into the stack and adding them. Then we need to take that result and make sure that's on the stack in the right place. Okay, that's cool. I thought I was going to have to add an extra parameter here. I've been looking at a couple of books for this, so I've got this crafting interpreters, and that's, I don't know if you can see this. I'm not quite sure where the camera is now, but this has got this similar idea of the stack frame that I'm using here. Not quite the same, but it's similar. They actually, when you call the function, this becomes a stack frame, and they don't have the return address like this. But they would make the stack frame, they'd make the stack frame look like this. Then when you return, you need to preserve the 5 and the 2. So they must have some pointer or some way of knowing that when we pop the stack frame, the previous stack frame, well, that's what they did. They have layered stack frames, so they always remember where they are. So what they actually do is they have 2 stack frames. This is the initial one. Like that. And then they have the new stack frame, which is like a sliding window onto that. It just looks like the original was contained inside this because we don't have anything else on our stack. But if we did have other arguments that were not passed in, then they would be outside of this sort of wider stack frame that we have. So maybe we can look at an example of that. So if our program, for reasons I don't understand, but if our program had, let's say, something like 3 plus 9, the instructions would then end up being something like push 3, push 9, and then it would be add. And then push 5, push 2, call 8. So we've got 1, 2, 3, 4, 5 new instructions. So that should be call 13. Okay, in that case, our stack would look like 3, and then 3 and 9, because I'm going this way. And then it would add them together. So you would get 12 on the stack, and then we push the 5, so it'll be 12 and then 5. Then we push the 2, which is 5 and then 2 on the stack. Then we do the call, so skip that. So in this example, can I do that? Yes, I can. Okay, in this example, that's the outer stack frame. It's the only stack frame we have, but it's the outer stack frame. Then as soon as we do a call, what we're going to end up with is we'll still have the outer stack frame, which looks like that, but we're now going to have an inner stack frame as well. It's going to start here because there are 2 parameters. And the return address, which would be 7, I guess with 5 off that now, so it should be 12. And I think that's it. Okay, this is awkward to see. I'm going to mark the inner stack frame with these parentheses. So that's the stack frame for the function, and the brackets, the square brackets, is the stack frame for the original stack frame for the outer program. And you can see that they kind of overlap here, so the function is sliding over, it's like a window sliding over the original stack. So then when we're running the function, our 5 on our 2 and our 12, oops, is our return address. And then we load -1, so we know this point. We still need to know this point somehow. Or we could track this point, I guess, swap the order back again. But either way, we end up trying to identify this value too. So we'll take that and put it in the stack. Let me close these brackets. And then we got 12, and then we start this. And we have 5, and then 2, and then 12, and 2, and then we load -2, so that's loading the other argument. And finally, we'll have 12, and then 5, 5, and then 2, and then the return address. I keep getting these numbers to be the same, which is quite annoying, but return address is 12. The add will pop two things off the stack and together, so we get 7 again. And then finally we hit return. It uses this for the instruction pointer. It grabs this and pushes it onto stack. So our outer stack is now restored. So 12, 5, and 2, but we also push the return value onto the stack. So we get that as the outer stack, and the inner stack is completely gone. So they don't need to worry about restoring the stack to the way it was, because they just go back to the original frame, which they know the start and end of. It's not quite the same as the way I'm doing it, so I'm not going to look at that. The other book I'm looking at is, I didn't share the screen for all of that. That's terrible. That's what I ended up with. There's a book I've been looking at is Modern Compiler Implementation in C. It's a bit different, so they do the stack layout, but this is all using registers. So the way that you pass parameters in with a register machine is you put the parameters into registers. So certainly you put the first few parameters into registers, because most programs don't have that many parameters. And then you reserve some memory to copy stuff into if you really needed it, but the hope is that you wouldn't need it. So you would avoid having to hit the memory to put stuff in the stack. You would just put stuff as registers. But I think this should work quite well. So we make sure we remember in our program where our stack starts. So for us, it would start here. Then we will use the offsets from this to grab values out of the previous stack. So we're going to make sure that things are set up correctly so that we can take our stack pointer and work backwards from there. Then we do whatever we want and we return. That actually means I don't need to change call at all. Maybe what I can do at this point is I can take this this whole thing, actually, this translated piece of code, so these instructions, put them into test, and then make sure we get this coming out the other end. Let's go for that. 1 second, sorry. I've got to bring the chat up for this as well. But I'm probably not going to find it now. Can I find it? 5. No, I can't find it from here. Okay, forget about it. Hopefully there aren't any comments. I'm not even sure anyone's watching, to be honest, but if you are watching and leaving comments, sorry, but I can't see them because I've messed up a bit. Okay, I'm going to grab this. I'm going to go to my tests. I'm going to write a whole test for functions. So we'll describe just, I guess, functions in general. This is not there. And we'll have a do. So what are we going to test here? We could say something like it passes values in and out. And then we will say do. I'm just going to grab this program. Paste in there. So program is going to be a couple of things. So we push the value. I think the way it's worked before is we push 9, and then we push 2. Maybe it's 3. It doesn't really matter though, because we're not going to use this value. It's just to populate the stack with something. And then we say vm.add. Okay, then we're going to push the values for our actual addition. Let me just write the program in some comments above it. Look at that. I can do comments. Okay, so we had something like fun, and I called it add, and it takes an X and a Y. Anyway, I don't have a syntax for this yet, so I'm just going to make one up. But I'm going to make one up that's short. So we can say add is X plus Y. And then we had the random instruction of 9 plus 3, which doesn't really do anything. And then we had calling add with the values 2 and 5. So that's what we're trying to implement here. So we got the random 9 plus 3. I'll make it 3 again just to match the code. We add them together. We're pushing. I want to do it this way around, I think. So 5 and 2. I think it's going to make my implementation a bit easier. Okay. So then we're going to. I'll leave the halt in place because that's always useful in the program. So we're going to do vm dot call, and then the instructions. So when we have call before, I've got call up here. Call position 3. So this is 1, 2, 3. No, it's not 0, 1, 2, 3. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then we get into our the definition of function. So this is going to be vm dot load, and then we're going to load the position -1, and then we're going to have vm dot load and we'll have position -2. Okay, it might not let me pass in -1, -2. We'll have a look at that in a second. So vm dot add, and then vm dot ret. What's this problem with this? This from -1 is out of the range of word 8. Okay. It's a bit tricky. I might add another command for this because I can't pass in -1 and -2. It's quite annoying. And I can't just leave 1 and 2 because that's how you load those positions out of the stack. So I'll go and take a look at that. The result of the program, the whole program, should be 7. Okay. Yeah, okay, so I'm going to do a new instruction. So in the VM itself, where are our instructions? These are instructions, okay. So for want of a better name, I'll just call it param. And that's equal to, not that, 0x08. And we'll put it into our list of instructions. And then we will export it. Okay. Let me just go back to my program. So instead of calling load, I'm just going to call param1 and param2. Save that. Okay, so it should be able to run this. It won't work. How do you run stuff? Is it Control-Shift-T? Yeah, looks like it. Okay. So this is failing with unrecognized instruction 8, which is what you expect because we haven't. Oh, I'm there. We haven't implemented it yet. So in our list instructions here, load takes a single argument, so it's going to be a unary thing, and it's going to be a step param rather than a step load. Okay, so otherwise, no. If the instruction is equal to param, then it's a unary thing, and it's going to be step param. Let's go and write that. Okay, so step param is of type. This is going to be a word 8 to, I guess this is the same type as before. And it's still going to be either type, going to be VM error or the CPU. Okay, so step param, it's got the address again. It's going to be very similar to the stuff above until we actually try and get it. We're going to need to stack, so it's going to be CPU at CPU. Then we're going to grab the CPU stack. And this is going to be equal to, okay, so we'll load the value. And this is going to come from, it's going to be s.load. It's going to be some kind of address. Don't know what this is yet. and it's going to load it from the CPU stack. CPU stack, and then we will return pure, and then we'll get a new CPU where the CPU stack is equal to, it's the same thing, so we just do s.push our new value v onto the old stack. Okay, so we need to worry about A, and for this we need to know the stack pointer. So it's CPU SP to get the stack pointer out. And it's going to take me a little while to remember how I set this up before. So when it's not calling return, it must be when we're doing call. Set the stack pointer to be the new stack pointer. A new stack pointer is position of new stack, and new stack is the return address pushed onto the stack. Okay, so stack pointer here is the position of the return address, I think, rather than position after it. I think position is just length. Yeah. So if I have 3 things on my stack, the length will be 3, obviously. But the stack pointer stack pointer will be pointing to position 3, offset 3, which is off the end of the stack. Okay. So we actually want to take the stack pointer, and if we subtract 1 from it, that's going to be our return address. So we'd actually need to subtract 2 from it. So I'm actually going to get that working, and then I will look at maybe modifying that a little bit so that the stack pointer is pointing to the return address rather than the place before it. But it's going to be a little bit fiddly. So I can say where, and then we'll just use this variable a. So that's going to be the CPU stack pointer -1. So that's now going to be the index pointing to the return address, and then we subtract the address from that. And it's a word 8, so we need to say, oh, what have I done? We need to say from integral, come on, letters of that. No. Cool. Okay, so we're working out where the pointer is at the moment, taking 1 off for the return address, and then we're subtracting whatever the value of address is from that. Okay. So go back to the spec. We'll probably get a different error now, a different failure. Oh my goodness, it passed. It passed first time. Did not expect that to happen. Okay. Cool. So I now have all the instructions I need to create this program, which is good, I guess. So next week, I guess I could start to look at writing the compiler for this. So something that compares multiple instructions like this, multiple expressions like this, with some kind of syntax and what it's going to be like yet, and can generate this instruction set, which is going to be fun. Okay, there are a couple of things that are not quite right with functions. One is that if a function calls another function, we update the stack pointer, but we can never restore it. So really, when we call a function and it calls another function, we should be pushing the stack pointer onto the stack. So one thing that might be worth doing, I don't know that because it's going to be a bit messy. There's another way I thought about doing the call. So we have this thing where we're just sliding our stack pointer over the other one, and then we're adding our stuff afterwards. So we need to know two positions. We need to know where our stack begins. Our stack should really begin here, actually. No, let's just do that. I was going to say we need to know where our stack begins, and we need to know how many things we have on it that are not part of our stack. But we don't need to know that because the whole lot gets thrown away when we return. So what I'd like to do is fix the code so the stack pointer points to here, where the cursor is, rather than to here. So the beginning of this stuff, in fact, if I can show it visually, what I want to say is that our stack pointer, right? Let's just no. Our stack pointer is going to be, let's represent it with a star. It's going to be here. Yeah, so I can easily add something after this. So this can still be the return address, but we can also add another value onto the stack, which is like the previous stack pointer. So when we call the function, we'll store the current stack pointer. It's a question of where do we store it? Do we store it in the frame of the function that's being called so it can restore it on the way out? Or do we store it in the call at the end of the frame for the calling function? I'm just going to quickly grab the compile implementation book because there is a convention in C, and the way it goes is you have local variables, then you have return address and temporaries and save registers. So the return address and then a static link. So the static link, I think, is the previous stack pointer. Next frame, I can't find where it is. I can't see in this book quickly where it's storing it. I think it's stored at the end of the frame. But at the end of the frame is actually start of the frame because the frames are drawn backwards usually. So it would probably be here. So at this point, we can store the old stack pointer, which is actually going to be 0. And then just if add called another function, then that function would begin here. So much for doing it here. I'll use different brackets for the new function. So it would have the old stack pointer, which is this position. So 1, 2, 3. It's going to be 3 or 4 depending which way you're counting it. Let me set it to be 4. Let me set it to be 3. No, I'm going to set it to 4. I'm going to start them from 1. In implementation, it'll probably actually be 3 because but if I'm calling the length of this, then it'll be 3. And if I'm storing this index, it'll be 3. So let's set it to be 3 either way. Okay, so 3, and then it'll have its return address. I don't know what the return address would be, but let's say, for the sake of argument, it's 22. And then you'd start to put other things into here. So this becomes the new CPU stack pointer, and this becomes the stack pointer to restore. Okay, so let's have a look at doing that. I think to do that, I'm going to rewrite a little bit about the way stack pointers work. So here, here, I can say it's, I don't know how to explain this, but it can call other functions. So this is going to look like I just copy a lot for now, and then we'll modify it. So let's call this function A, and it could be recursive. I mean, I don't see any reason why not. Is there any reason why not? I think that would be all right. There's no reason why we couldn't have recursive functions, I don't think. Might mess me up a bit. So we could actually say, let's just double y. So x plus, or we'll just add some value onto y for no particular reason. So all right, this function so the end result, I guess, is going to be 9 because we've added 2 onto the second argument. In terms of the instruction set, so we're all good up to the point which we call halt. And then what happens here? So we get our first parameter. And then what we want to do is we want to call A with 2 parameters, and I'm flipping the order of parameters around. So we actually want to push 2 onto the stack at this point. Being a compiler is quite tricky. I can see why they made computers do it. It's just going to be straightforward push. Whoops. And then the value 2. And then we're going to load second parameter. And before we add them, we're going to call our function. So this is vm.call. And the address is exactly the same as before because it's a recursive function. So we call position, we call program at 12. Oh, no, it can't be recursive because then it'll just keep calling itself. Oh, obviously, it's not going to work. Okay, so I'm going to make this B, I think. So we'll define B. And that's going to be a function called B, which takes 2 arguments. Again, we can call them X and Y. And that's going to be equal to, right, let's just pass one thing into here. And pointlessly, this will just be, let's say X plus 2. Let's do it that way. Okay, so we're not going to call 12 anymore. We're going to call a new address, and we're also not going to push 2 on there. So we just get the second parameter. We're going to call a new address. Then we're going to add the result together, because that's still what our program does. Okay, so this new piece of code, this new function is going to go at the end. So this is going to be vm dot, I need more screen. Let's work out the call first. Sorry, so we're going to call 12, which is here. So this is 12, 13, 14, 15, 16, 17, 18, 19, 20. So it's going to be call 20, and then the definition of B is to load parameter 1, push 2, and then call add. Other way around, but it doesn't matter because addition is commutative, so I'll ignore that question for now. So we're going to have vm.param, and we've only got one parameter here, so it's going to be 1, and then we're going to have vm.push, and then 2, and then vm.add, and then finally return. Return. Okay. The result should still be 9. I think this will not work. I don't know what it will do, but I think it will not work. We got invalid stack position. Okay. Doesn't work in that way for some reason. Nope. Okay, so what time are we now? We're almost 10 o'clock. Let's see if we can do the first part of this. So this is when we call something. With 2 parts of this. So when we call something, we also want to push the old stack pointer onto there. And I want to push it on before I push return address, I think. So we're going to push return address onto the keywords are hard. The result of pushing the CPUSP stack pointer. stack, so I'll need to also pull this out. So this be CPU SP. I'm actually going to change it a little bit. It's not going to be the position of the new stack, it's just going to be the position of the old stack. So new stack pointer is the position of, this is going to be CPU stack. Okay, so return will now need to change. So return value result of calling the function is just popping the last thing off the stack. That stays the same. Now I have this s.ret. I maybe want to use jump instead. So I want to do a couple of things. I want to get the value from the stack at position CPU SP. And then I want to get the value of the position after that. And that's going to give me my new stack pointer and my return address. And then I want to ditch, like I want to truncate the stack to be just the stuff before that, and then I'm going to push stuff onto it. Okay, so I get my result. That's okay. I've got a load instruction, so I can use that, I think. So, what should we do? We can say, I guess the new stack pointer. What does load return? Oh, load doesn't. Yeah, load returns a single thing. This is going to come from s.load, and we're going to load what are we going to load from here? We're going to load the position of CPU SP. From the CPU stack. Okay. We no longer need this second value, I don't think. I'm going to optimistically assume we don't need it. Okay, so we load the new stack pointer, and then we can get the new instruction pointer as well. And that's going to come from s.load, and then this is going to be CPU SP, nope, +1, again from the stack. We don't need to modify the stack now, we're just grabbing values at the middle of it. Okay, so we have our return address, we have that, and then we want to do that. Oh, I need to pass the stack into it. So I just deleted some random characters there. So this is going to come from CPU stack. Okay. We can just get rid of that line. This is going to be CPU, no, it's going to be new IP. Then we'll restore the stack pointer. So CPU SP is equal to USP. Okay, now we need to worry about this S, which is the new stack. So we could just tell it to drop the frame. I'll write a new instruction for this, even though it's really just calling take. But we can say S comes from take the stack, and we will say drop frame. I think that makes sense. Drop frame. We'll give it the stack pointer and the stack. Okay, so now in drop frame, sorry, in the stacks, we can get rid of this return and jump stuff. Actually, is jump the thing I want? I think it is. Yes, so I can just call jump, I think. Let me go to this one first. And I'm going to export jump. And that. So calling drop frame, I can just tell it to jump. It's not quite the right thing, but it's close enough. It's not a good name, I don't think, for what it's doing now. That. Okay, pretty sure this is not going to work. We also have some failing tests. So we've got stack spec and it's probably got return in it. Yeah. We need to rewrite this as being the implementation of jump. So what's this doing now? Jump is going to take, we say jump to 2, it should just be the stack 1, 2. Should be good. And then we can just grab that and change it to be jump. Okay. I imagine this is going to work, but let's give it a go. 4 failures. Okay, so calling the function doesn't work. That doesn't work. Return, I need to rename this, but no, return errors to the stack, so I contain return address. Okay, stack jump is wrong, but only because of the ordering of stuff. So stack jump is doing the thing that I expect it to do, but returning is not, it seems. Oh. Okay, so this one is easily fixed. But there's something wrong with the way return is working. Let me get VM spec and have a look at return. Here's the stack is empty. Header does not contain return address, so that's not quite, it's not really how it works anymore. Because it doesn't make sense to call return now without calling call first. So these ones, well, the first one's kind of okay, I guess. But this one doesn't make sense because there's stuff on the stack, but it's not the right stuff. There's not really enough stuff on there. It just works. Hopefully it will work, but I don't think it does. But we call position 3, we push 5 on, we call return. Does that work? Let me look at the failures we get. Function call functions doesn't work yet, that's okay. And passing values in and out. I know why this is broken, which would also explain why the other one's broken as well. So when we said load param, we got this -1 to compensate for stuff, but that's not the case anymore. Okay, so what happens to do this? One failure. We're getting so close now. Okay, functions are not calling the functions properly, but passing values in and out is now working again. So it's possible I got the answer wrong for this or the code wrong for this. We have a quick look at it, but it's looking kind of promising. VM spec. Okay, so what we're doing here, we have our nonsense 9+3. I might just get rid of that. We don't need it. It's just complicating things. It's got to break all of my indexes. That's a bit annoying. But I've done it now. Okay, so we can't call add either. So the way this works now is we push 5, then we push 2, then we call A, and this is now 1, 2, 3, 4, 5, 6, 7. So it should be calling 7. Okay, and then we stop at the end of the program. For function A, what we do is we load parameter 1, then we load parameter 2 because it gets passed into B. Then we call, I need to fix that address, so this is 7. So this is 7, 8, 9, 10, 11, 12, 13, 14. So now equals 14. I think that was wrong before then. Position 14. So we call B, and then we add the result of calling B. Now that's tricky. No, it's not tricky. It is tricky. Okay. Bit of a problem with the way I've done this. So we load this value to so that we can call this function, and then it's going to return the results of the function, so in this case 7, but we've still loaded y onto the stack, so we still loaded 5 onto stack. So our stack for this function will be 2, 5, and then the result of this, which is 7, and then it will try and add, it will call add, so it should be 7 plus 5, which is going to give us 12 back rather than 9. Is that what we got? Yes, it is. Okay, what I actually need to do is worry about the order of stuff. should actually... I wonder what I should do. Thing is, if we're loading these just to call a function, then we should be throwing them away when we're done. Right, these don't exist on the stack when this function returns, when we finish calling it, basically. So actually this 2 and the 5 belong to the frame of A rather than belonging to the outer frame. Now this is tricky then, because I need to know I can't just take push 5 and push 2 and then move them into my function, because these instructions don't belong in my function. It's just a result of evaluating them. So if this was more complicated than 5, if this was something like, it doesn't have to be very complicated, does it? I could just say like 5 plus 3. That 5 plus 3 does not belong in function A. It belongs here. So I need to evaluate whatever these instructions are and get those onto the stack. The fact that it's just pushing stuff is not particularly relevant. It doesn't mean we can just pick it up and put it in our function. But I want the result of this to be available to this function. Okay, I'm going to leave it here because we were running slightly. Next week I'll come back and I will have a think about this. A couple of ways I can think of doing it. One is, at this point, you specify the number of parameters. So you could say there are 2 parameters to this, and then when we return, we can use that value 2 to say, okay, additionally pop 2 things off the stack before returning. So we could do it like that. The other way is to copy stuff. So we reserve part of the stack just for copying variables into. So param1 would not be loading from the outer frame. It'd be loading from this special area where we copy parameters into, and then we throw it away. So our stack would actually have the original stack pointer, the return address, and then after that it would have some space reserved for the parameters we're using. So we would copy the params into here. Seems very wasteful to copy stuff around, but it would be a way of solving this. And then this, the stack that we're actually using starts after here. So if you said load parameter 1, we'd copy it again. And you said load parameter 2, we'd copy that again. And then when you add them, it would get to 7. And then it would use this as return address. Grab this as the old stack pointer, grab this as the instruction pointer, and then ditch all of this stuff. But it seems like an unnecessary copy. So I don't know whether or not I want to go down that route. I'll also read a bit more about this, see if there's a good answer without using registers. Cool. Okay, but that's it. I'm going to leave it there for tonight. Thanks for watching along. Sorry for the bit in the middle where I forgot to put it back on the screen. I just left it on the camera. And apologies for my typing tonight, but it's kind of been fun. I'm starting to get the hang of this layout a little bit. Anyway, next week my typing should be better, and yeah, hopefully we can just finish off this last bit of passing parameters in and being able to do that multiple times, and not just assuming it's the last 2 things on the stack. So yeah, we can finish it off Then maybe I can go and start to look at how to write the compiler to generate these instructions from this program. Cool. Well, thanks for watching and see you next time. Goodbye.